everyone. It's my great pleasure to introduce Christina Kudazzo, who will be giving a short introduction on two speakers. And I'm very happy to have you here, and let's have a great day.
So it's my pleasure to be once more being a speaker today. So Mor is a scientist working in LIFMET, very close to us. And she's working on non-nuclear polarization for some time now. So she will be presenting you some novel perspectives on glycolysis, hyperpolarized carbon-13 MRI, deuterium imaging, and that in force. I know more for working a lot on carbon-13 MRS and on hyperpolarization, and I'm very curious to see what she will present on deuterium imaging and on the Then some details about Mor. So Mor, let me look here. So yeah, no, I did look here. So Mor did her PhD in chemical physics at the Lausanne Institute in Israel. She got her PhD. It looks like she got a prize for her PhD. And then since after her PhD, she's here in the LIFMET, working as a postdoc and as a scientist. I'm mainly working on Colonization. So no more, I'm looking forward to see your talk and luck.
So thank you, Christina, for inviting me, and thank you. It's a pleasure to be part of the CIBM Breakfast Science and to present a bit of my research to our neighbors here in the building, but it's a good opportunity to show you a bit what we are doing at the LIFMET side. And a bit about my MRI journey, like Christina said, I studied in Israel. I studied chemistry in Tel Aviv University and working at the lab of Professor in Lausanne. I had the opportunity to get some hands-on experience in NMR and MRI, and I learned how to practically use this machine back then. As Christina said, I then moved to the Weizmann Institute in Israel. I did a PhD with Mr. Friedman. Then I was focusing there. I was working more on MRI physics, more on sequence development, what we call ultra-fast NMR. And there I also did my first hyperpolarized study in vitro setting. After my PhD, I came here to the LIFMET with Wolf Grutter, and at the time with Mor, with the aim to know how to do NMR experiments in vivo. I learned how to perform preclinical research in MRI, and then, of course, to do hyperpolarization in preclinical settings. So with all this expertise I acquired over the years, I developed my own research line, which is aiming to develop MRI modalities to interpret what we call the biochemistry. And why we should look at biochemistry, we're entering what we call molecular imaging. And when we are doing morphological imaging, we are looking at the shape, and like we just heard before by Paula, we can learn a lot of information from the morphology changes. The idea to move from morphology to biochemistry is that we directly look at what is happening at the cellular level, which enable us to improve the diagnostic, to select better the treatment, to identify better how the treatment works, and we go to more what we call personalized medicine. Sorry. So we know molecular imaging more in the context of that. This is the most applicable technology, which is widely also used in the clinic. And the idea in my research is to exploit MRI, which is non-invasive, non-radioactive, and to develop it into molecular imaging. So the way I look at MRI, I look at it as a multimodal technology. If we look at water, which is a very strong signal, we can get a lot of information related to the morphology, related to function. If we get rid of this huge signal of water, we can get what we call spectrum of the metabolites that are in the brain, and we can quantify concentrations of metabolites that are there in the tissue. We can also exploit MRI to measure dynamic. We can measure very fast metabolic changes with hyperpolarized tracers, and we can also learn about slow biochemical processes using thermally polarized labeled molecules. So my research is coming to take advantage of all these rich modalities to develop MRI into molecular imaging with the focus on studying brain biochemistry. More specifically, my interest is to learn about dynamic processes, with MRI, and for this we are doing what we call MRI tracer experiment. We take advantage that in the body we mostly see protons in vivo, but if we take other NMR active nuclei, what we call X nuclei, and we take a molecule that is interesting in terms of metabolism, and we label a specific position, we could then track how it's converted through the biochemical process. So here, for example, glucose downstream with glycolysis, it will transfer the labeling, and then we could track with the chemical shift. It's a specific property of NMR or MRI or MRS, whatever we want to call it, that we can identify each molecule, and each molecule has a specific position. It will appear in our detection. So we can measure fast metabolic processes with hyperpolarized MRI. We can learn about slow metabolic processes with thermally polarized MRIs. So most of my research is focused on hyperpolarization. And what is the idea in this experiment? We take a molecule that is interesting for us biochemically. We boost the NMR signal of this molecule. We then insert the bolus of this molecule to our patient, and we follow in real time, meaning it's maximum couple of minutes, 3 minutes. We follow what is happening to the tracer we injected in vivo. What is it good for? Here you can see an image of a patient with prostate cancer. You can see here, it's a good time to have a laser pointer. Voila. So here we have a tumor that is showing in hyperintensity in a T2-weighted image. And when the same patient, what happened? We have a break. So when the same patient was taken to hyperpolarized pyruvate experiment, suddenly some abnormalities appeared in both sides of the prostate. So you can see here, there is the tumor that we had before, but also on the other part of the prostate, there is some abnormality that was later approved as a tumor. So going and moving from morphology into metabolism enable us to measure modification and changes that are there before any morphology or structural change appeared. Because the changes in the biochemistry is much prior to change in morphology. So this is how we do hyperpolarized experiment at LIFMET. We are using what we call dissolution DNP. It's important to say that there are many different modalities we can get hyperpolarized signals. They exist. There are also some of them becoming more and more commercially available. Here at the LIFMET, we are focusing on what we call dissolution dynamic nuclear polarization. And what I will show you is a typical day at the lab. So here you see Alicia. She's holding a Eppendorf with a solution containing the molecule that we're interested and the polarizing agent. She created these little pearls, these little beads, and now she's carefully, in liquid nitrogen, she prepared them and she carefully transferred it into the sample cup. She collected her beads, and now carefully she's placing the sample cup inside what we call the sample holder. And with this holder, she will insert, here's Alicia again, taking the sample and carefully inserting the sample into the DNP polarizer. Here the polarizer is the 7 Tesla polarizer that is coupled to the CIBM 9.4 Tesla scanner. She's connecting a microwave source. With the microwave irradiation, we will be able to transfer polarization from the polarizing agent to our molecule. She's turning on the microwave, and now we have to wait. Once reaching maximal polarization, Tan is coming to help Alicia to perform the precious dissolution. Alicia is turning off the microwave, disconnecting carefully the microwave source. Now she's taking out the sample at the microwave guide, and she's entering the dissolution stick and push your positive red button and work. Yes, success. So we have a hyperpolarized signal that was detected quickly at the scanner, and we are all happy. So as I promised you, what we saw here is how we do the experiment. In my research, I'm more focused on brain biochemistry. So we have to select this specific molecule to interrogate biochemical processes in the brain. And luckily, the brain has the blood-brain barrier that protects it from many molecules to enter. But for us who want to put a molecule that will enter the brain to measure biochemistry, it's somehow challenging because most of the molecules will not enter the brain. And it's important to say that when we are studying pathology with this technology, we have more possibilities to choose the right molecule because many pathologies are associated with the break or some functioning of the blood-brain barrier. Of course, looking at the healthy subject, we are more limited. Yes, we do find molecules that could be hyperpolarized and relevant for studying brain biochemistry. We just need to make sure that the molecule that we choose will have sufficient signal also after it enters the brain and converted through the biochemical process. Luckily, over the year, we could find different tracers that enable us to look on brain biochemistry. With hyperpolarized acetate, we show that we can directly detect a TCA cycle intermediate alpha-ketoglutarate, which is more known as, which is also 2-oxoglutarate. It's positioned in a very interesting place at the TCA cycle because it's the one connecting between energy, metabolism, and neuronal activity. 2-oxoglutarate will then lead to the production of glutamate and then glutamine. I was also part of the team developing the first non-persistent radical of completely endogenous preparation of hyperpolarized pyruvate. For those who know a bit hyperpolarization, pyruvate is the gold standard contrast agent for molecular imaging with hyperpolarized probes. And then we develop a protocol to use lactate. Lactate is interesting in terms of brain because in some situations, the brain will even prefer to use lactate as a fuel rather than glucose. And with the group of Florence here, who is studying lactate neuroprotection of stroke, and like Jean-Elias from the HLSSO, we develop a collaboration to see how can we use hyperpolarized lactate as a theranostic agent for stroke. So we will give hyperpolarized lactate in a therapeutic dose, and we will be able to give some treatment to the patient after stroke, and at the same time to measure the metabolic changes that are consequence for this bolus injection. Last but not least, the main focus over the year was to study hyperpolarized glucose metabolism, because glucose is the primary fuel mode for the brain. Basically, the brain needs glucose to maintain the normal activity. Many pathologies are associated with changes in glucose metabolism. And we showed for the first time, basically the unique to enable to detect hyperpolarized glucose metabolism in the brain. We then apply this protocol to study a very unique model of glioblastoma, infiltrative compartment of glioblastoma, and we show that opposed to what we expect in the tumor mass, in the infiltrative zone, we actually see reduction in glycolysis, and this we could detect with hyperpolarized glucose. We then see how we investigated how anesthesia will influence glucose metabolism, and recently, we were founded by the FNS and in collaboration with Yuhei Takado from Japan, and with the aid of Andrea, we are developing a completely new setup, completely endogenous setup to study Alzheimer's disease metabolism with hyperpolarized glucose. So, as I said, the main focus was on glucose, and what we wanted to see how glucose is changing when we are changing, how glucose metabolism is modified with consciousness. And the way we are modeling different consciousness states is by playing with two different anesthetic protocols. Let's look at glucose metabolism as this big red box. So we have the glucose that is entering, it's passing in this machinery, glycolysis, and it's exerting lactate. So let's look at glycolysis as simplified as that, and keep in mind that we look at MRI as a multimodal technology. So the first thing that we can do, we can look at the pool size of lactate. We don't give any glucose, we just look how lactate concentration is different when we use these two protocols of anesthesia that are giving us two states of consciousness in the brain. So as we expect, when we use isoflurane, which is a deeper anesthesia than the other one, we see increase in lactate, which is something which is known of the use of isoflurane. However, when we use melatonin isoflurane, which is a common protocol, let's call it protocol 2, it's a common protocol for functional MRI in rodents, we see a huge difference in the lactate pool size. These are the most striking differences that we see in the proton spectroscopy. There are hints of changes between creatine and phosphocreatine, yet it's not significant, and all these measurements were performed at a 9.4 Tesla. It's hard for us to say with resolution to what extent we can explore the creatine phosphocreatine ratio. When we look at the hyperpolarized data, we see something completely different. We give hyperpolarized glucose, we see how much hyperpolarized lactate is produced from this hyperpolarized glucose, and after 1 minute, we see a different behavior. Actually, in the deeper anesthesia, in protocol 1, the black, we see less lactate that is produced compared to the one that we see in somehow lighter anesthesia, the protocol red, and we see increase in the lactate signal. See much more lactate that is produced with the lighter anesthesia. So being a bit confused with these two results, we ask ourselves what should be the labeling of lactate at the steady state, because with the DMP or with the hyperpolarization experiment, it's not only for DMP, we are entering to look at the pre-steady state. It's a non-steady state case. So we ask ourselves, how can we see what is the lactate labeling with at the steady state? And for that, we develop a deuterium imaging, which is based, which enable us to monitor the labeling of lactate at the steady state. So here we will take a molecule. It's a general scheme for thermally polarized experiments. So again, we take the molecule that is interesting for us, we label it. At this time, the signal is much lower. We are using just a small, tiny thermal signal. We will insert it to our patient. Oops. And we will follow over time, which means a couple of hours, 1 or a couple of hours, and we will follow what is happening to this tracer over the time. Why we were targeted on deuterium, it's because the great potential of deuterium MRS to become a clinical relevant technology. It was recently, although it was recently demonstrated how it is possible to easily apply deuterium imaging in clinical environment. So going back to our experiment, we are back to our red box of glycolysis. This time we have deuterated glucose entering, exerting deuterated lactate, and this is what we see at this time. So we have here, actually, when we have the deeper anesthesia, we have higher lactate. Somehow surprising, maybe not. Interestingly, in the lighter anesthesia, we don't see any lactate that being produced. So we add all these different evidences and different behavior of labeling of lactate from glucose through glycolysis. So we ask ourselves, what's going on? So I went to an expert of the CIBM to answer tough questions. And together with Bernard, we developed a simulation to give us information. What is the parameter that is more relevant for the imaging of, for the production of lactate when we use hyperpolarized glucose? So going back to our red box with the hyperpolarized case, we have hyperpolarized glucose entering, passing to the machine, exerting hyperpolarized lactate in 1 minute. Two parameters can be relevant, is how fast we are consuming the glucose and what is the initial pool size of the lactate that is already there. And this is the base of our simulation. So what you can see here, this is the input function, this is the bolus of the glucose that we give. And the first thing to do, we say, okay, lactate concentration has no influence. We fix the lactate concentration, the pool size. We just change, we see what is the labeling, the signal of the lactate when we change the glucose consumption rate. And here you can see when the glucose consumption rate change, there is a big, this is 60 seconds, like the 1 minute when we detect, we see a huge differences between the lactate signal that is proportional to that is coming from the change in the glucose consumption rate. We then repeated the simulation, and this time we said, okay, glucose consumption rate is not the important factor, it's actually the lactate pool size. We fix the glucose consumption rate, and then we change the lactate pool size. Looking at 60 minutes, we don't see much difference in the labeling of lactate. To be more fair, we even added different losses that associated with the signal in the hyperpolarized case, meaning the relaxation time, which is related to the lifetime of this non-equilibrium signal, as well as the RF pulses that we use to detect. And when we add also the losses that are known to us in the experiment, we can see that the change due to the glucose consumption is the one that is governing the change in the lactate signal, and the pool size becoming even less important in the experiment. So we conclude from this simulation that the important factor in the labeling of lactate is glucose consumption rate. So this was our hypothesis, and then we said, okay, but we have a way to measure glucose uptake. So again, running to Bernard, we talked, okay, how shall we do the experiment? Let's do FDG PET. So this is not glucose, it's a glucose analog, but it enables us to have information about the uptake of glucose. Because in the PET, we can define a certain timing at which the tracer that we inject is only corresponding to the first step of glycolysis, which means that what we detect is really what was observed by the brain. This is happening at 50 minutes. This is the steady state situation of the brain. So these are typical images that we get. We have to say that the different consciousness state, the different anesthesia protocol that we use have some effect on physiology. This is why we choose to match the glycemia, which has a strong effect on glucose uptake. And what I'm showing you here are two images when the glucose concentration is hyperglycemic. You are reaching the maximal concentration that all the glucose transporters are saturated, to be fair for the analysis. And what you can see here, that in steady state, it's hard to say that there is a difference, but 10 minutes, which is the case which we are not yet in steady state, it's a pre-steady state case, somehow it's a bit hard to see just from the image, but I trust you that you might see this lower uptake in the case in the blue protocol, in the black protocol, compared to the lighter anesthesia. So let's put together all what we have so far. So when we look at the pool size, let's do a separation between the steady state information that we get and the non-steady state information that we get. So when we look at the pool size and we focus on looking at glucose metabolism, we know that there is increase of lactate when we use the fluoride. It's a deeper anesthesia. When we look at the steady state labeling, you can see here the group analysis. When we look at the steady state labeling with deuterated glucose, when we use the deeper anesthesia, isoflurane, we have higher lactate that is produced. When we look at the uptake at 50 minutes, which is the steady state of the PET experiment, it's a preliminary result, but it seems consistent that there is no difference in the uptake of glucose analog. Looking at the non-steady state, the very early steps of the metabolic process, when we look at the hyperpolarized glucose, this is 1 minute to glycolysis, we see much stronger lactate production, which is significantly higher lactate production when we have lateral anesthesia compared to the isoflurane, which is also hinted by the pre-steady state images. This is the first images that we can get after 10 minutes with the PET, but we see less uptake when we have isoflurane. So this is an important slide because it shows you that with hyperpolarization, we have a clear access to what is happening before the steady state. We are not measuring a reflection of the pool size. We're actually measuring another parameter, which is also different than what we get with the thermally polarized tracer experiments of MRI. And what is nice with the hyperpolarized MRI is that we have a clear distinction between what we injected here, the glucose, and what is produced, what is the consequence of the metabolic process. And this lactate is far with 12 steps, 12 biochemical steps from the tracer that we injected. We can see some hints from the PET, but in this case, the signal that we see, it's very difficult to say whether it's the tracer, is it the tracer in the blood, is it the tracer in the tissue, or if it's actually the first step of glycolysis that we are teaching. So with the hyperpolarization, we have the unique advantage of NMR, the chemical shift, and we have also the possibility to look at other compartments of biochemistry, which are not accessible with the thermally polarized modalities. So hyperpolarization, if we just take the take-home message, is here to complement what we know from other modalities, and it can give us information at stages that are not accessible with other MR modalities. So before I conclude, there are many people who were part of my journey over the years, and a very special thanks to Tan, who is here in the audience, and to Emma, that was doing a PhD, of course, to Andrea, different members at the DNP team. Special thanks to Bernard, who is all the time willing to think with me on the stupid question I come. And thank you for the attention. And talk is open to discussion.
So I have some questions while Valerio is thinking. Thinking what is he doing here, but until he's I go ahead. Okay, so I have two questions for you more. The first one, I saw deuterium spectrum, and I had to go out and come in, and maybe I missed how is the deuterium acquisition, but on the 9.4, what type of sequence did you use?
So at the time, because we wanted to be consistent, we did an experiment. 9.4, we gave a bolus of deuterium with the same setup that we use for the GP. We have a coil that is a surface coil localization. So at this stage, we did an experiment like that. So we have sensitive and the same brain region as independent.
So no localization, just as a
at this stage is no localization, although we do have a sequence ready for us the 14 delta to image and deuterium. Hopefully, we're looking forward to the 9.4 upgrade to be able also to do it on the 9.4 Tesla. Again, one that already it would be very nice to be on the same settings. We are developing, we have some basic techniques here. So these are the kind of coils we already have for both deuterium and carbon, and also some other designs that we are waiting for the parts to come to have a more efficient imaging.
How relevant is this kind of a sequence which is not localized? How relevant is for your injecting deuterium goes everywhere? And yes, glucose goes everywhere. How relevant is it to acquire one is not localized?
I think that is a very good question. It's also about the timing, because when you do hyperpolarization, you measure over 1 minute. But we know we don't have background. Systemic effect, which is extremely relevant, and it's not different. And it's true that when you do deuterium, you cannot neglect, because in the 1 hour detection that we do, glucose is passing in the liver and circulating. And
It's about some at the blood.
Yes, it's definitely true. And this is why we are really making a lot of effort. And actually, the title slide, and go back there. It's an example of an image of hyperpolarized.
Yeah, I remember when I was doing nitrogen Yankee and nitrogen chloride, the main question was, are you sure that it's not coming from the blood? It's the boxes are so big over there, the point spread function is everywhere. So,
and you see here, this is the images that Sam recently acquired at Fortin of hyperpolarized pyruvate metabolism. And you can see here in the green, it's pyruvate. This is one of the hybrid. It's another chemical form.
No, the blue is lactate.
The blue is lactate. The lactate.
And this is lactate.
This is lactate.
Pyruvate.
Yeah. So you can see here, you can measure the images when you have pyruvate, lactate, and the ratio. And it's so true that we do need to move the imaging. Now we are adapting this protocol to be able to image that.
It's not necessarily about imaging, it's about polarization, because imaging is such big boxes, constant function, you get behind there and say, my point of view, but yeah. And then the last question, because of the virus thinking.
One on Zoom.
Yeah, so the last question is for the PET experiment. How are the data processed? The maps looks very nice, but is there something wrong with the processing then? Just the maps which come from the scanner.
So at this stage, what I showed you is the zoom.
Yeah, exactly.
And this like the zoom map that I then we started with this protocol. And it's not a very sophisticated imaging. It's zoom map, long filtering. This is what you see.
I know so well. So this is why I'm asking the question, because I know
and it's very, very interesting because of the huge differences that we see in proton spectroscopy, deuterium, hyperpolarization, and now possibly with the PET. We started the discussion with Bernard and Jesse to try to see if we can get access to the kinetic information at the 50 minutes. And it's something in general moving into quantitative analysis also with the hyperpolarization and the PET. It's something that we are digging toward. And hopefully after the ICMRM, we sit together with Jesse and Bernard to see how we can implement the
Jesse is busy, so Jesse needs to finish her PhD. However, indeed, she really, so yeah, just because I know it. It's not, but she developed a very nice tool and a very nice program in MATLAB and everything to really fit and go to CMR glucose and not the SUV maps.
Yes,
so,
exactly. This is
so you will be using her resources then. So that was the question.
That was the idea to continue the collaboration and to see if it's something that's interesting for all of us and it makes sense.
Okay,
but,
good.
We will not postpone her PhD.
Yeah,
this is not the idea. We don't want to do that.
I guess you don't have that power now. But the question.
And it's recorded, so I have no way back.
I just wanted to know from clinical application, this affect like the anesthetized patients that during the MRI supposed to be whatever. Should we be, I mean, how much different would be in anesthetized and non-anesthetized patient and try to analyze kind of metabolic changes?
It's a very, very good question because usually patients, they are not anesthetized. But in some very specific cases, you don't have a choice.
Yes.
So it's a very relevant question, and I hope one day I will have access to clinical setting as well to dig into this question because it's something in the discussion we every time we ask ourselves what is the difference. And actually my collaborator in Japan is working a lot with awake animals as well as Valerio, so there are a lot of resources here to try to do the thing maybe in awake animals and to see to what extent the anesthesia, because it's a drug, it has an effect. We see it in the physiology. We have to match the glycemia. So it's totally important questions. And hopefully step by step, in a couple of years, I could tell you something about that.
Maybe along the same line, actually, just a very simple question. So at some point, when you were showing the data on the different lactate peaks on the different anesthesia level, and you said that there's a huge difference, and to me, it didn't really look like a huge difference. It was just a small peak. So if you would quantify it and give it a number on the difference between the, the amount of lactate that is now being metabolized, is it something we should worry? Like, is it really unphysiological, or?
So I just want to go back to this slide.
Yeah.
So we have the picture together with.
If you have to.
So here is the group analysis, and this is. I admit that also for my poor eyes, I don't manage to see the numbers, but those differences are significant. So when we have isoflurane typically, and it's something that we know from isoflurane, most probably it's not a brain-burn lactate, but rather a blood-burn lactate that was transported. And we did also, I didn't show it here, we did some experiment with regular lactate, that we gave a bolus of lactate in this 2 anesthetic condition, and it seems that there is more transport of lactate when we use isoflurane. It's a question that is out there. There are different studies, and also with the diffusion weighted spectroscopy, there were different evidences to show that the lactate that is produced in the isoflurane is not something that is coming from the brain, but rather coming from the outside. Forgot the name of your collaborator from
Julien Valette, exactly. Looking at the extracellular intracellular. He's suspecting that the majority of lactate who comes with extracellular, and he is trying to prove it by diffusion weighted spectroscopy. But lactate, especially in the mouse, it's very much brain region dependent. If you go in the striatum, you'll see a high peak of lactate. However, if you go in the hippocampus or in the cortex, provided that you don't have lipid contamination, that you will be considering as being lactate, the lactate peak is small. It's really a brain region influence also in the mouse brain. And sometimes we've not so much seen the rat brain.
So maybe I missed it, but that means that during anesthesia, there is a switch from normal glycolysis to, so they use less.
What we know,
was it more lactate in neurons to, or they use less? Like, I missed a little bit.
I think also when we use the anesthesia, we're also affecting the entire balance. And for example, what we see when we just switch the anesthesia, and some experiment that we did from isoflurane to medetomidine, the glycemia level is very different. In the isoflurane, you stay still on the normal glycemia. With the combination of isoflurane and medetomidine, you reach extremely hyperglycemic conditions. So overall, there is a change. It's hard to say because we get to a new metabolic steady state after 1 hour. There is the entire body, the entire arrangement that is changing, and also that will possibly influence. There are so many things that can also influence. If it's the transporter, we don't know if there is a change in MCT activity and distribution as an effect of anesthesia. We know that it can be very rapid because we saw it also in the stroke analysis that 1 hour after stroke, there is a change in distribution of transporter that will be the one that's responsible to transfer monocarboxylate molecules like lactate. There is a lot of open questions. So,
last question from a very old friend for some of us and a continuous friend for the others. Hey, so I think I have a question.
Yes, thank you very much for this very interesting talk, Mo. I have a question about pool size. You mentioned that lactate pool size is not a major factor in case of hyperpolarized glucose, right? I'm wondering, do you have any idea about the case of hyperpolarized lactate experiment? Is it also the case for that hyperpolarized lactate injection?
So what we know about, I have to be honest, we don't know about hyperpolarized lactate specifically. We do know about hyperpolarized pyruvate from other groups that are in the field, that the rate limit, the factor that is the most important for the success of the experiment is the transport of the monocarboxyl, the pyruvate. Even if you have high pools of lactate, not necessarily in an experiment of hyperpolarized pyruvate, you will see it in the tumor. Because if there is no modification of the MCTs, it means that the lactate or the hyperpolarized pyruvate will enter the tissue and then could exchange with the lactate pool. When we look about hyperpolarized lactate or hyperpolarized pyruvate, we're more focused on a specific portion in glycolysis, or perhaps indirectly measuring glycolysis, because we are entering really to the end product of glycolysis. And what we know from other group study in different models, also in the brain, is that the transport, as well as you showed and we showed together for lactate, that the transport is the rate limiting factor in the experiment. And then, depending also on the polarizing agent, it's a recent work we did with Stan, and it's now out there under review. Different factors may influence, but the rate limiting part is, in this kind of experiment that are very rapid, is the transport.
Thank you very much.
Yeah. So now I guess that we are more or less done. I think that there's no more questions for today's talk. Thank you very much for the two speakers. Really, really nice talks. And see you next time in 1 month for the next meeting. I don't know if Pina would like to add something.
I'd like to invite the two speakers to the front because we have some gifts for both of you. Maybe you have to stand there, and Christina as well. So don't leave. So this is a token of our appreciation. Thank you so much. And also for Christina, who is leading and playing an umbrella, helping to play an umbrella role in the CIBM. So thank you very much once again. And stay tuned to the next one. We're a bit over time, but it's okay. We will have the croissants in a very, very fast way. And please join us next time on site.
Yeah.
Thank you.
Bye.